Our first interdisciplinary paper will be thermal sizing of a lunar rover using SimCenter 3D. That will be presented by Jean-François Labrecque. And since we're already seeing the first slide, I take it you're here, so let's go.
Thank you, Brent, and good job on the pronunciation. No, Jean-François was not easy for many people. Hello, everyone. Thank you for attending this presentation today. So today we'll be talking about thermal sizing of a lunar rover using SimCenter 3D. Before I get started on the presentation itself, I just want to tell you very, very quickly about who we are as Maya. We're a Siemens partner, and we developed thermal solvers amongst many other things for the Siemens software. So we, for example, developed TMG, which is the solver used in the background in the space system thermal module within SimCenter. And we do services as well. We have many customers. We do consulting, training, mentoring, and stuff like that. So that said, why would we do the thermal sizing of the lunar rover? Why would we do a study about that? Was the question about the speakerphone for me? Sorry, I just saw this pop up in the chat, so I just want to make sure the sound is okay. No, I'll try to speak closer to the microphone, so just to make sure. So as I said, why are we working on the lunar rover? Why are we doing a study about that? Well, right now, as you all know, the Artemis program is has really ramped up the interest about moon exploration. And nowadays, it's not only a NASA concerted effort, right? Most of the workload is still at NASA, but there are actually many smaller companies in other countries and smaller startups as well doing projects to send rovers to the moon. So we have several of our customers right now working on applications like that. And I have to say that most users, most people who will develop rovers and technology that will be sent to the moon in the next few years do not necessarily have the whole of NASA's technical heritage. We have access to NASA's thermal guidebook for moon analysis, moon thermal analysis now, which is very helpful, but it's a lot to digest. So one of the objectives of this study here was to provide a methodology and template for our users to show how to do this type of analysis within SimCenter. And second, we also wanted to investigate what we can do within SimCenter. Oops, okay, sorry, I have some notes about audio not being too good. It was okay on the demos I did the other day, so I'm hoping it will be corrected. I'm hoping it's stuff for everyone. So I have the same setup as for the other sessions. So I'll just try to move in closer. Hopefully that will help. So we want to see what we can do without user subroutines. And user subroutines, they're essentially when you want to do programming with an API to access the thermal solver directly. And with that, you can access some of the variables, modify values during runtime, and you can do many things, but it's something that's a bit complex to do, because you need to have some programming experience, you need to do either Fortran or C++. It's a bit more complex. And I'm sure in big agencies and big companies like the Lockheed Martins and Northrop and Sierra Nevada of this world, you're bound to find people who wear both hats, mechanical engineer and programmer. But in smaller companies, people don't have that kind of expertise, and they don't necessarily have the time also to investigate that. So we wanted to see what's possible without using any of the subroutines, with using only what's directly accessible from within the solver. Yep. So for this study, we've just used a custom mission. We've used a very simplified CAD of a CAD that was developed by Bijay Balia-Hembra. He did that for NASA context. So we really simplified it. We really wanted to focus on the process here. And in our custom mission, we wanted to look at the operations over the first lunar day. So we deployed the wheels, we drove out to the landing platform. And over those operations, we want to monitor the energy that's available over the full day. And that will give us an idea of how much energy we have available at the end of the day if we want to survive lunar night. Because most of those smaller companies or the new missions, they won't be using radioactive sources, so they'll need to rely only on that collected energy. We also investigated the impact of different latitudes, landing at different latitudes, different landing times. We've looked at landing on the Maria versus Highland. We've used expressions to parameterize that study. As you can imagine, just looking at the CAD, this rover, it wouldn't make sense to land that rover at very high latitudes because the solar panels are pointing up, so you really wouldn't collect much energy at high latitudes. But it's, again, we're just focusing on a workflow here, not as much on the results. We developed a thermal model for that. If you attended the presentation on Wednesday, it was Tuesday actually, we actually showed how we developed that model from the CAD. It's a pretty simple model that we use. It's really a system level analysis that we're doing at this point. We use solar panels with an efficiency of 20%. They're pretty big panels. It's a big rover. We set those boundary conditions using expressions, as I said, just to do a parametric study under different boundary conditions. And we had to do a bit of a fancy setup to monitor the energy collected by the solar panels and to be able to use that value to parameterize the operations afterwards. If you're using a user subroutine, you have access to the directly to the energy absorbed by those panels. If you don't, the one variable you have access to out of the box is to use temperatures during runtime. So we just use a very simple setup where we collected the energy on the panel behind the solar panels. So the solar panels have some transparency, and knowing the capacitance of those elements, we were able to get the total energy absorbed. We used also a surface template for the moon. So let me just talk about that really quick, because that's very important boundary condition on the moon. We need to be able to capture the surface temperature properly. And 2 years ago, NASA published their thermal analysis guidebook for the moon, which had some very interesting information, very useful about the moon surface temperature, optical properties, subsurface heating, and so on. And we have two models that we've used in the past to represent the surface from the short course that they've provided on Wednesday under guidebook. I believe that we're in line with what they've done. So our simple model is just a flat surface with zero thermal capacitance. It fluctuates very fast. As you can imagine, if you just leave it floating as is overnight, the temperature is going to be 0 Kelvin because it has no thermal capacitance. So what we do for that simplified model is we apply a sink temperature on the surface overnight. And for the daytime temperatures, we let it stabilize. It's essentially a steady state because it has no thermal inertia. And we compared the results from that simple model with the temperature set that we got from the LRO diviner, and that's from the processing from the Williams and Al, as you can see from the figure on the upper right. And what we observed is that it's not too bad during daytime, but there are some limitations. Some of those, just to mention some of those, the accuracy is pretty good at lower latitudes, but as you approach higher latitudes, like the landing sites of the future Artemis missions, this simple model for the moon surface doesn't work too well because the temperatures at the higher latitudes are really strongly affected by topography, by craters and mountains and so on. So you really have to account for that. Well, first for that topography, so you would have to import realistic surface models, and also for the heating coming from the subsurface. And we do have a more complex model that takes that into account. We haven't tried importing the real surfaces yet, but this is something we'll look into in the near future just to test it out. One other thing that you can observe from this plot is that the dawn-dusk transitions, they're not too good because the software by default doesn't account for solar occultation. So in reality, the sunrise and when the sun gets down, it's a really slow process on the moon. So you have some heating that's slowly ramping up and ramping down at the start and end of the day. We don't reproduce that with our out-of-the-box solar heating, so you would need a user subroutine to really account for that properly. All that being said, let's look at the results now. So this just shows basically the kind of results we had for one simulation. So we're looking at the deployment operations, as I said. And it's really one thermal simulation here in which we simulate those operations here. So there are black body view factors, solar view factors, albedo view factors. They're all updated during the simulation every time the model changes. So as you can imagine, it's a pretty slow simulation typically, but since the model was pretty small here, it actually ran pretty fast. It was an hour and 15 minutes to compute all of the view factors and to solve for temperatures over 15 days on the single core and not using restart options, not reusing the black body view factors from the previous run. So that was relatively fast and it performed well. I think that's a slow motion effect. And on the right here, what you see is the energy actually collected by the solar panels over the day. So the latitude at 0 degrees on the highland is really the best case scenario in terms of energy collection. The sun passes directly overhead, and we have the perfect angles, let's say. And at the end of the day, the energy that we collect with that, this is approximately 1/3 of a battery of an electric Hummer. So it's really not that much energy, but it should be enough to provide maybe 50 watts of heater power over 15 days. I imagine it would be more for a big rover like that, but it gives you a quick idea. And obviously, we're not addressing some of the big issues with surviving the lunar night, because one of the big issues that you have to evacuate the heat during the day, and then you have to really be insulated overnight. So we're not addressing that right now. We're just looking at the energy collected. Using this model here, so we were able to look at the energy collection over a full lunar day at several latitudes. As I mentioned earlier in this presentation, as you can imagine, at higher latitudes with the solar panels pointing up, the energy collection is really not that good. It's not a good design for that. And we also looked at landing on the highlands in Maria. And for the Maria, we activated walls on the side to make sure that we didn't have any solar flux until an elevation of 20 degrees, just to see if we could easily do that in the software and see what the impact would be. The impact is actually pretty small, those walls, because well, when the sun is really low, you don't have much collected energy. So it doesn't change much on the energy collected. I expect it would change more on the temperatures, but for the energy collection, it doesn't change a whole lot. And now the next step is we started looking at the energy collected, but against the landing time now. So if you look at the graph on the left side here, we're looking for a latitude of 0 degrees at different landing times. The furthest one would be at 6 in the morning local time on the moon. So at sunrise we land, and up to noon, approximately landing at noon. And then we look at the energy collected over the whole day. So that again, that gives you an idea of how much energy you have at the end of the day with just a very simple model quickly done. And we did the same thing at different latitudes versus landing time. So this shows you a whole 3D plot of, let's say you want 50 watts overnight over 14, 15 days. How much, what are your options? What's your possible landing time? What's your potential latitude of your landing site? So it was essentially a quick parametric study to show what we can do without using any user subroutines here. And if you wanted, you could take this module and just start adding components on the inside and do anything from there. So in conclusion, in this study here, we developed a simple lunar rover using our software. And at the end of the day, what I did is I used GPU ray tracing for the black body factors. So the runtime was actually under 10 minutes, which is pretty good for a quick parametric study like that. Our simple template is a good approximation for lower latitudes, not so much for higher altitudes. And I have to say that it's not a full study in that I didn't really look at the impact of shadowing on the surface. I expect if you would have a still object for a very long time, then the region that is shadowed by that object, the temperatures would probably be underestimated, because we don't account for that subsurface heating with a simple surface model. The slow motion effect performed quite well. I have to say it's a bit complex to set up the first time, especially for complex operations like that. But it worked well, and it was actually pretty fast, at least for a simple model like that. We did find some limitations when not using subroutines with those out-of-the-box tools or objects within the software. One, I don't see it here, is the solar occultation. So we don't properly capture the heat flux from the sun at sunrise and sundown. One thing that bothered me a bit is the energy that we collect. It can be used directly in a conditional expression. So it goes a bit with the second comment here. My original intent when I did this presentation or started this study was to look at the energy that's collected and perform operations based on the energy collected within one single solution. And it turns out that without any user subroutines, you can't do that. You can't use expressions inside of solid motion effects, so inside of those movement constraints, essentially. And it was interesting to note, maybe we'll look into implementing that in the future. For this study, what I had to do was to split essentially the simulation in several parts to be able to use conditions based on the energy collected. One last thing also is that deactivating elements is not straightforward using conditions. It's very easy to do directly within the solver, so you can just, it's just essentially one click of the mouse. But if you want to do that based on conditions, it's a bit more complex. So I ended up using journals, which are just a recorded sequence of operations for this process here. And I have to say that user subroutines would probably facilitate complex operations in a case like that. But from what I've seen in this study here, the software handles that pretty well, and we'll be able to provide more information to our customers in the future using the customers that are using this software to do lunar analysis. So that concludes my presentations. Do you have any questions?
Oh, we have time for a little bit of questioning. If we have any, please post them in the chat. One question to start us off. This is a neat project. I always find templates like this useful. I'm curious about how you would use something like this in Maya. Is the vision that this would be an example model that users could modify, or is it something that can be built in where they're filling out a form with their rover size and coordinates where they want to go, and it generates a model off of that? How would this integrate with the platform?
We do have templates that we use. You could start the model from a moon surface template, for example, so that we can provide. And we can provide those two levels of complexity that I've described. So anyone who wants to do an analysis, we provide a template that will have the moon surface, which includes for subsurface heating, which has those fields for the temperatures overnight if you want to count for that. So that's already a starting point. We can also provide starting models to do some of the analysis where people would just modify the geometry and add their own components on the inside. Something that we do is we do consulting services. So we do have customers that we're helping out with their analysis. So we would use also that for our own customers. Doing this study is beneficial to us as well in the work that we will do for the thermal analysis of lunar rovers in the future. So many uses for that. And it also tells us what the limitations are. So what, for example, that solar occultation, this is something that I think we'll need to look into if we want to really get more precise results.
And one more question. You got a good comparison to a more elaborate model. Did you have any field data that you could compare against also?
Field data, how do you mean for the temperature of the surface?
Yes, something from a previous lunar mission. I'm not sure if there's something that exactly maps to your situation, but I'm wondering if you came across something you were able to compare against.
One thing we've done in the past is there is some data available from the Apollo missions for the temperature. And we've looked at modeling very simple geometry on the surface of the moon and looking at the temperature of that geometry, not of the surface directly. So this is something that we've done in the past as well. And it correlated quite well, but again, it's close to the equator, those temperature sets that we've looked at. So I did not actually do any real, and that's compared against real data for landing sites close to the poles, which I think would really be the interesting thing to do at this point. So something I'm thinking about doing in the future is importing that full topographic model as we've seen in the short course the other day, and plug that into the software and do analysis with that. Although I'd have to find some interesting data to correlate with. I don't know how much data we have for temperature of components close to the poles. I'll need to do some research for that.